Hello and welcome to the sixth and final part of Lesson 4. Lesson 4 has been quite a long lesson. So in this part of Lesson 4, we're going to solve the Navier-Stokes equations again using our four-step protocol. Now the flow that we'll examine is going to differ from the previous example, and we'll see how to treat flows where one surface is open to air. Now we're going to approximate this by assuming that there's no shear force applied to the fluid at the open boundary because of the difference in viscosity between air and a liquid, which is going to be something of 5 orders of magnitude. We're also going to include the effect of gravity in this problem, and we'll see how solutions to some flow problems can be constructed from essentially summing two different solutions together. So the first thing I'm going to do on my blackboard is to draw a diagram. The diagram I've drawn is of a belt, and that belt is immersed in a viscous liquid, and the belt is oriented vertically. So one side of the belt goes up, one side of the belt goes down. The side of the belt goes up drags some fluid up with it, and it's that we're interested in. So I'm going to zoom in my diagram on that rising surface of the belt. The belt is now going upwards at a velocity v belt, and on the surface of that belt is a thin layer of fluid. We're going to assume that this layer of fluid is uniform in thickness, and that thickness is of a value delta. We're also going to assume that this flow is steady, is long established, there's no time variation. Now let's think about the pressure acting on the surface of this fluid. If we think about this belt, the fluid on the belt is exposed to atmosphere at all points, and so there's no pressure gradient upwards or downwards on that belt. If we think about moving into the belt, we'll see probably that all the fluid's either moving up with the belt or down under gravity. So all the streamlines are straight and parallel, so there's no pressure gradient across those streamlines either. So let's think of some physical properties. I'm going to set my density equal to 1,000 kilos per cubic meter and my viscosity equal to 100 Pascal seconds. Again, this is really cold honey type viscosity. So let's do step 1 of my solution protocol. I'm going to write the Navier-Stokes equations down. There we have them. And I want to justify setting the substantive derivative on the left-hand side, big D by big dt, equal to 0. So I'm going to do that this time by looking at my flow geometry. I can see that the film thickness is uniform, that the fluid is either rising in the y direction under the action of the belt or falling in the y direction under the action of gravity. And so there is no spatial acceleration in this geometry. I've also assumed that my flow is steady and not changing with respect to time, so there is neither temporal nor spatial acceleration, so therefore I can set the substantive derivative on the left-hand side to 0 and end up with a nice simple equation there at the base of the board. Fine. So that's step 1 complete. Let's move on to step 2. Now that I have my simplified vectorial form of my equation of motion, I'm going to think about what velocity components I've got and how they change. So let's look at the problem once again and say, well, I'm going to describe my velocities in a Cartesian coordinate space because I've got no curvature. This is not a cylindrical problem or a spherical problem. It's just rectangular. And if I'm going to do that, I'm going to have velocity components Vx, Vy, and Vz. Now, I'm going to place my Cartesian axes on the surface of the film. The reason why will become apparent in a second. And so upwards is positive y. So that's actually the direction in which the belt's moving. And so I can say quite reasonably that I expect the velocities in this problem to be moving in unison with the belt. So the only velocity I expect is going to be in the y direction. Moreover, that y direction velocity is only going to change in x. It would not be unreasonable to suggest that what's happening on the surface of the fluid might be a little different in terms of velocity as to what's happening on the belt. And so by allowing a spatial variation in the x direction gives us leeway for different effects to happen. But I only have my y direction velocity and it only changes in x. Now let's think about my gravitational acceleration. According to the coordinate space I've defined, g acts in the y direction, and the only non-zero component of my gravitational acceleration is downwards in the y direction. So my gravitational vector just consists of one component, which is minus gy. So Recognizing that, I can take step 3 of my solution protocol and simplify my Navier-Stokes equations and drop them into the relevant coordinate system. The only non-zero component of my gravitational force, the body force, is going to be in the y direction, so I'm dealing with minus rho gy, and the only non-zero component of velocity is going to be vy, which changes as a function of x, so from the Laplacian term I only have d2vy by dx squared, so that is step 3. Now let's think about step 4, which are boundary conditions. So, where I've placed my coordinate axes on the surface of the film, I'm going to assume that I got zero shear stress, because the shear stress imposed by the air on the film is going to be negligible. The shear stress, remember, is related to viscosity. The viscosity of the air is tiny compared to the viscosity of the liquid. It's 5 orders of magnitude lower. So zero shear stress is a pretty good approximation. Remembering Newton's law of viscosity, tau equals mu du dy, if I've got zero shear stress, tau, I'm going to have zero velocity gradient dvy by dx, which is very similar, if not identical, to what we found on the centre line of my pressure-driven flow. There, my velocity was at a maximum. Because of that, I had a turning point, so the derivative of that velocity profile was 0. So, in effect, what we have in terms of a potential velocity profile here is a half a parabola going into the flow towards the belt, because at the surface of the flow, I have 0 shear stress, which means that dvy by dx equals 0. Let's think of a second boundary condition. I have one of no slip. The fluid is stuck to the belt where the fluid meets the belt. However, the belt is moving upwards, and so at x equals minus delta, delta is the film thickness, my coordinate axes are on the surface of the film, positive x is moving away from the film, so the surface of the belt is at x equals minus delta. My y direction velocity is going to be equal to the wall velocity, in this case the belt velocity. So vy equals v belt at x equals minus delta. So those are my boundary conditions. So having identified my boundary conditions, having simplified my equations of motion into just one second order ordinary differential equation, I can now integrate. So there at the base of the board in pink, I've written the first integration step. I've taken rho gy onto the left hand side to remove the minus sign and also divided through by viscosity. Furthermore, I've written my second derivative of velocity with respect to x as d by dx of dvy by dx, and taking the dx over to the left hand side too. So the integral of rho gy over mu with respect to dx is equal to the integral of d of dvy by dx. And if I do that first integration, I can see that on the left hand side I have rho gy over mu multiplied by x plus my integration constant c1 is equal to my velocity gradient dvy by dx. Now, with cunning axis placement, I know that my velocity gradient is equal to 0 at x equals 0. So therefore c1 equals 0. So that's why I've placed my axes on the surface of the flow, because it makes c1 very easy to evaluate. Let's do the second integration step. So there's the equation I've just arrived at. I've taken dvy by dx apart, and I'm integrating the left-hand side now with respect to dx, and all I have left on the right-hand side is just dvy. So integrating, I get rho gy over 2 mu x squared, plus a second integration constant c2 is equal to vy. So we need my second boundary condition to evaluate this second integration constant, and I know that the velocity of the fluid moves with the belt at the surface of the belt, which is x equals minus delta. So if I substitute those conditions into my result from the integration step, I can see that my second integration constant c2 can be written as v belt minus rho gy over 2 mu delta squared, which allows me to write my velocity profile vy as a function of x as at the base of the board. And this is really interesting because we can see we've got 2 bits added together. And what I want to do in the final part of this little bit of lesson is to investigate physically what's going on here and investigate why we've got two parts added together. It's always important to get through to the physics of a problem and not get lost in the mathematics or just take the mathematics without a physical understanding. So, there's my solution consisting of two parts. Let's see what these two parts are telling us. If the viscosity is very high, and we said it's 100 pascals second or so, then that first term on the right-hand side of my velocity profile, which has a pre-multiplier of rho gy over 2 mu, could be neglectable. So, for high viscosity, Vy simply is roughly equal to the belt velocity, which means that all the fluid is moving upwards with the belt speed and there's no variation of velocity in the thickness of the film. We've essentially got solid body motion. So that is one limit, the high viscosity limit. Let's look at another limit, which is going to be, well, what happens if the belt is stationary? If V belt is equal to 0, then the fluid is going to drain down under the action of gravity, which is that first term. So gravity is acting as a body force, and at the belt there's going to be a no-slip boundary condition, and the belt is now stationary. At the surface of the flow there's a no shear stress boundary condition, which means the velocity is at a maximum. And we can see we've got 1/2 of a parabola now resulting from that draining flow. And the final solution is simply a sum of these two solutions. And so we can see that if we're neither dominated by viscosity and if the belt is moving, then you've got a combination of both of these solutions together. And so the intermediate solutions result from gravity draining and belt lifting. So let's summarize a few key points. In this final part of lesson 4, we've solved the Navier-Stokes equations again for the hybrid flow of a high viscosity fluid being lifted by a belt, but also where that fluid can drain down the belt as well, because the belt is vertically oriented. We saw that careful axis placement allowed easy incorporation of the boundary conditions. We saw that in this case, due to the action of body forces and the no-slip boundary condition at the surface of the belt and the no shear stress condition on the fluid surface, the draining flow had a parabolic velocity profile. However, we saw that the lifting flow, the flow that was moving with the wall, was linear, and we ended up with effectively solid body motion. And we saw that intermediate solutions are effectively just a sum of these two phenomena.